If you hand me a braid on some number of strands, I can make a knot out of this just by connecting up the ends of my braid. So here's a braid on 2 strands. I can make this into a knot by forming its braid closure, and the braid closure will just connect the first position of the top of the braid to the first position in the bottom, and the second position in the top of the braid to the second position in the bottom, and so on and so on. So we're just connecting the like positions from the top to the bottom, just joining them up, tying them together, right? And in doing so, we're either going to get a knot or we could potentially get a link. It really does depend on how the braid is actually permuting the positions from the top to the bottom. But if we take the closure of a braid in this way, we're either going to get a knot or we're going to get a link. And so what I'd like for you to do is just real quickly with your team, take a couple of very simple braids on 2 strands, starting with this one, which is just the braid S1, but also investigate the braid S1 squared. Find their braid closure and figure out whether or not you're looking at the unknot in each case, or whether you might be looking at a different knot. So this is going to give us a way of connecting in braids into our ways of thinking about where knots can come from. All right, so this was a nifty little activity that gets us some exposure to how braids give rise to knots. So we started out by forming the simplest of possible braids, right, where all we do is put in a single positive twist in here. I think positive. Let me make sure I'm getting the orientation of mine right here. So we have a single positive twist. This is the braid on 2 strands, which we can call S1. And we form the closure of a braid just by connecting the tops and bottoms of the first positions and the tops and bottoms of the second positions. And you noticed in this example that when we did that, what we got was something that kind of looks like this, right? Whoops, let's stay together here. But if I have a diagram of something that looks like this, you can rightly claim that that's actually just an unknot, right? It's a diagram of an unknot. It only has a single crossing. And all it takes is a single type 1 Reidemeister move to just untwist and demonstrate that we had an unknot to begin with. So the braid S1 is just braid language for an unknot. So it gets more interesting if we have more interesting braids to work with. So as soon as we get to S1 squared, so if I do a single twist and then I do another twist, now I have this braid on 2 strands. It has 2 positive crossings. When I connect its top and bottom positions, notice the top and bottom are both the top and bottom of the same strand now. I'm connecting a red to a red. And the top and bottom of my second strand are a green and a green. And of course, mine aren't going to stay together now because I'm on camera. I connect the tops and bottoms of the greens. And what I end up with is, first of all, something that has more than one component, right? I have now a 2-component link. And moreover, I have a 2-component link that is linked together. I can't separate these two. I'm not one of those, it's not one of those classic magic tricks with the split rings where you can just sort of hit it on the table and it falls apart, right? There is no isotopy that I can use to separate these two. This is the simplest possible example of 2 linked components, and it's called the Hopf link, H-O-P-F, the Hopf link. It's a 2-component link that is minimally linked to one another, so it's not an unlink. As you might expect, an unlink would just be copies of the unknot which don't have any crossings with one another, and it looks something more like that, right? But that's not what we have here. S1 squared actually forms a link, 2-component link called the Hopf link. So we could play with this some more. We could say, what about the third power? Right? If I take the third power of S1, make 3 crossings. There's 1, here's 2, here's 3. If I were to do this, let me try and pull this tight if I can. So now I have these 3 positive crossings in my braid. When I connect the tops and the bottoms, notice that once again I'm connecting red to green and green to red. And so I'm not going to get a link anymore. I'm actually going to get a knot again. And it looks like this knot is not one that I can sort of separate together to make an unknot. Like whatever isotopies I try to perform on this, I can't manage to untangle them. So I get something which is essentially knotted and which has 3 crossings in it. And that might be a clue as to the identity of this particular knot. It's got 3 crossings and it's not the unknot. So it's probably the 3-crossing knot that we met earlier on in our hour today. I even think it's an interesting question to ask, when do we know that the closure of a braid is even going to form a knot in the first place instead of a link? So that might be a question for you to think about with your teams, right? In this example, if I only have 2 strands to work with, it seems like if I have an odd number of positive crossings and then I form the braid closure, I'm going to get a knot. But if I have an even number, like I have here, if I had 2 crossings, right? Now when I form the braid closure, I'm connecting a red to a red and a green to a green, and I'm going to have a 2-component link. When I had an odd number again, I end up connecting a red to a green and making a knot. But if I went to a 4th crossing and I connected tops to bottoms, now I'm connecting greens to greens, reds to reds, and I have a 2-component link once again. So for 2 strands, there's kind of this oddness, evenness question about whether or not the braid closure gives me a knot or whether or not it gives me a link. But it's a more interesting question if we ask, what is the result? What does the pattern look like for braids on any number of strands? So that's kind of an interesting question to sort of roll around in your head over the course of the next week. But taking the braid closure of a braid is a very important source for where knots and links can come from. And in fact, there's a theorem that says that it is the only source for where knots come from. That every knot that you can give me, if I just sort of cram all of its crossings over to one side and then comb all the other strands off to the other side, I'm going to be able to see it as the braid closure of some braid, right? Every knot that's sufficiently nicely behaved, every what's called a tame knot. Tame knots just mean that we can't have the crossings infinitely accumulate on one another or some crazy thing like that, right? If I only have a finite number of crossings, I definitely have a tame knot. And every tame knot is the braid closure of a braid on some number of strands. So every knot comes from a braid, and every braid can be made into a knot using this construction.